Hey, good morning, guys. Assalamu alaikum. Welcome back to grade 11 physics/chemistry by Inspired Teens. Where in today's lesson, we are going to be continuing with, we're going to be starting stoichiometry or quantitative aspects of chemical change, whatever fancy name you want to put to it. Okay, so yes, we are going to start this. And obviously, I will we'll have our catch up on Monday. Sorry about last week again. I wasn't feeling too well, but all good now. So we'll have our catch up on Monday. I sent out the time. I forget exactly what time it is, but I think it's like 11 or something in the morning. So yeah, we'll obviously continue with stoichiometry there. And please note that we will continue with our lessons throughout the holiday. Okay, so please do attend. It's once a week, and I think it will really be beneficial for you guys to just stay up to date and to keep the ball rolling. All right. If with regards to extra lessons in the holidays, I'm not sure. I will confirm if we're having those, if we really need to, I suppose, if we need to catch up on something. But by the end of the holiday, we're gonna try to be on par with syllabus. Okay, so that going into term 3, we can start with term 3's work. Okay, cool. Let us start. Grade 11 stoichiometry. Okay, so we're just gonna read through all of this just to get a better understanding of all of these little concepts, that all of the different types of concepts that we need to learn and know for this section before we will get into calculations as we go along. So the mole, let us discuss the mole. Atoms, molecules, and ions are too small to count, and there are so many particles in even the smallest sample of a substance. Now, this is where I read that fact that I mentioned the other day, well, a few weeks ago at this point. There are more particles of water in a teaspoon than there are teaspoons of water in all of the oceans. There are more particles of water in a teaspoon than there are teaspoons of water in all the oceans. That's crazy. Okay. Right. Rather than dealing with the particles individually, we deal with a special number of particles called a mole. The mole is a name for a special number. Many numbers have names such as 2, pair, 3, hat trick, 12, dozen. The mole is a SI unit. 1 second, sorry. The mole is the SI unit for the amount of substance. A mole of particles is the amount of 6.02 times 10 to the 23 particles. That number is known as Avogadro's number. Avogadro's number is a large number, is even too large to imagine. That's how many zeros it has. For example, this many grains of sand piled on the surface of the earth would reach the moon. The mole is defined as the number of particles or atoms in 12 grams of carbon-12. Okay, so the mole is the SI unit of the amount of substance. A mole is a particle, is the amount, a mole of particles is an amount of 6.02 times 10 to the 23 particles, which is known as Avogadro's number. Okay, it is defined as the number of particles in 12 grams of carbon-12. Okay, so however many particles is in carbon-12, 12 grams of carbon-12 specifically. So again, these are really high numbers, right? Particles are extremely small. Okay, they are extremely small. So if you want to consider even just 1 gram of a substance, let's talk of a substance that we know, I don't know, like table salt, NaCl, right? Give me 1 second, sorry. Okay, so yes, what was I saying? Okay, so particles are really small. Okay, so when working with the amount of particles, like I said, if you consider even 1 gram of table salt, right, the amount of particles that are in there, right, it's like unfathomable. It's to be able to comprehend the amount of particles that are in these small amounts of substances. Okay, it's impossible to comprehend. Okay, so imagine bigger amounts of substances, larger amounts of substances. So that's why these constants and these units of measure and these SI units were developed. Okay, for example, Avogadro's number, right, represents so many particles. Okay, and even further than that, a mole, when we consider a mole of a substance, so it's a constant that scientists many years ago decided on, okay, to measure out different elements and different compounds, okay, using this mole concept. Okay, so 1 mole, okay, of any substance, so let's just say 1 mole of aluminium, for instance, okay, the mole is defined as the number of particles or atoms, okay, in 12 grams of carbon-12. So however many particles there are in 12 grams of carbon-12, again, so this, it might seem random to us, right? 12 grams of carbon-12. Carbon-12 is just an isotope of carbon, okay? And 12 grams of it is a really specific number. Why? Okay, it's just because that's what they decided would work best as 1 mole. So basically, 1 mole of aluminium contains the same particles, same number of particles as 12 grams of this specific carbon isotope of carbon-12. Okay, it's isotope, just a type of carbon. Okay, it's not important for now. You guys have probably learned it before, but again, it's fine. You don't really need to know isotopes anymore. So it's fine, right? So yes, okay, and just to clarify, an isotope is a compound with the same number of protons, but different. I'm pretty sure it's a different mass, the different atomic mass. Okay, so yes, 1 mole of aluminium contains the same amount of particles of 12 grams of carbon-12. 1 mole of anything would contain that same amount of particles. So that's why they decided to, they settled on this unit of measurement. That's how it works. Okay, so we just that's just for extra understanding purposes. You just have to know the definition of a mole, okay, and Avogadro's number, and so on. All right. So the mole again is defined as the number of particles or atoms in 12 grams of carbon-12. Okay, so that's 1 mole of anything. Right, let us move on. Let us talk about molar mass. Okay, molar mass. Particles are too small to weigh individually. Molar mass is defined as the mass in grams of 1 mole of particles, atoms, molecules, or formula units, and is measured in grams per mole. Okay, so again, these particles, okay, they're too small to weigh individually. There are so many thousands, millions of particles in even the smallest amount of a substance, or an element, or a compound. So to measure each individual particle, it's not possible, right? They are too small. So that's why they decided again on these constants, right? To measure a larger amount of these particles, right? If we combine more and more particles of the substance, now we can measure it and really define a mass for it, type of thing. Okay, so molar mass again is defined as the mass in grams of 1 mole. So the molar mass that you see in your periodic table, which I believe can be found here. Okay, if we look at our periodic table, right, where's our molar mass? Yes, at the bottom. At the bottom, these show us the molar mass. These show us the molar mass like this. Oops. This and this and this. All these bottom numbers, these show us the molar mass. Okay, so what is this molar mass? This is actually the mass, okay, of 1 mole of hydrogen. The mass of 1 mole of hydrogen. Okay, so let's go back here. All right, and let's continue. So let's discuss molar mass. Again, I'm going to define it. Molar mass is defined as the mass in grams of 1 mole of particles, okay, and is measured in units, the unit grams per mole. That's why it's grams per mole, because it's how many grams in 1 mole. So again, they decided on this constant for the mole. Okay, why? Because particles are too small to consider. There are too many particles to consider. So we defined it as, okay, let's group up a bunch of particles in a certain, of any certain element, okay, or compound or whatever we're dealing with, right? And 1 mole is defined as the same number of atoms or particles in 12 grams of carbon-12. So that's how they defined 1 mole, and that's how we do calculations, right? And now, again, the mass of a single particle is too small to consider, so we considered the mass of 1 mole, which has the same amount of particles as 12 grams of carbon-12. Okay, so that's what molar mass is, the mass in grams of 1 mole of a certain substance or whatever we're dealing with. Right, let's look at relative atomic mass. Relative atomic mass is the average mass of an atom compared to the mass of carbon-12. Okay, it is measured in atomic mass units. Molar mass of an element is equal to the magnitude of relative atomic mass in AMU. This is found on the periodic table. See the table below for other substances. Okay, so relative atomic mass, we don't really need to use it to its calculation in this at this level, but what's interesting for us to note is that relative atomic mass, okay, is actually what these are. If you remember from grade 10, where you calculated relative atomic mass, okay? Now, relative atomic mass, you had different isotopes of a certain compound. So maybe you had carbon-12, carbon-13, carbon-14, for instance, right? Carbon-12, carbon-13, and carbon-14. That just means that in this world, okay, in the nature, okay, in nature, carbon exists in 3 forms. This is an example. I'm not speaking factually, okay? It's an example. Just say carbon has 3 isotopes, 12, oops. Carbon has 12, 13, and 14. Isotope carbon 12, 13, and 14. This means in nature, carbon may appear with a mass of 12, then a mass of 13, then a mass of 14. Okay. And then we use that percentage calculation to calculate an average based on what percentage they occur. So maybe this occurs like 90. It's a lot of the time this happens. This occurs 99.5%. Right. 99.5% of the carbon in the world is carbon 12. And then maybe 0.3% is 13 and 0.2% is 14. So obviously, when we calculate an average between this, considering their percentages in the world, we are going to, the average is going to be extremely close to 12. That's why we just consider the molar mass of carbon as 12. Because when we say the average, right, considering the percentage that it occurs in nature, okay, carbon-12 occurs 99.5%. So the average is going to be very close to carbon-12. So for example, if this was the correct percentages, right, and then you calculate the relative atomic mass, that's how you got 12. So you need to know that all these masses in the periodic table, okay, these are the relative atomic masses that have already been calculated. That's why it says here approximate relative atomic mass. So what we know as the molar mass is actually the relative atomic mass that has already been calculated and put here. So these are all relative atomic masses considering all the isotopes of the elements that exist in the world. So for example, aluminium, we get to 27 because we considered all the isotopes that exist in the world. We calculated the average according to the percentage that they exist in nature, and we got a relative atomic mass of 27. Okay, so that's what we need to know, right? The molar masses are actually relative atomic masses calculated already. Okay, so that's why I'm going to read again. It says relative atomic mass, or AR, is the average mass of an atom compared to the mass of carbon-12 atom. It is measured in atomic mass units. Molar mass of an element is equal to the magnitude of relative atomic mass. This is found on the periodic table. See the table below for other substances. So for example, here, type of element, type of substance, it's an element, atoms, example, neon, formula Ne, molar mass is 20, covalent compound, carbon dioxide, you add them up, 12 plus 16 plus 16, because molar mass of carbon is 12, oxygen is 16, we have 2 oxygens, so that's how we get that, NaCl is that, Au is that. So this is just using the periodic table to calculate the molar mass. At this level, that's what we want to achieve, right, which is fairly nice and simple. Okay, so that's what this is basically explaining. Okay, let's do like this example. What is the relative formula mass of calcium sulfate? And yeah, so basically what you're going to do is you're going to say, you're going to calculate calcium carbonate, calcium, okay, plus sulfur plus 4 times oxygen. Okay, we don't have to consider relative atomic mass, that we just know molar mass from periodic table, right? So I'll just do one of them. Calcium, or we'll just do the molar mass, because again, relative atomic mass, not really important at this level. Calcium, sulfur, and oxygen. So calcium is 40, sulfur is 32, oxygen is 16. Calcium is 40, sulfur is 32, oxygen is 16. So 4 times 16. We add all of these two together, all of them together, we get a molar mass of 136 grams per mole to the -1. What do you do? That's 64, 71, 64, yeah. Okay, so I hope that makes sense. And yeah, that's basically molar mass. That's the simplest calculation that you're ever going to do in stoichiometry. Okay, so now with that we know molar mass, let's discuss a concept called percentage composition. Okay, so with percentage composition, percentage of element is equal to total M mass, molar mass of big M is molar mass. By the way, did we discuss the formula? No, sorry, I forgot to discuss this formula. Okay, so let's have a look at this formula. This is the formula that includes moles. Its number of moles is equal to the mass in grams divided by the molar mass. Okay, and the mass in grams is small m, and the molar mass is big M. That differentiates them, and it's important to note. Okay, so mass of a substance in grams, the molar mass. Okay, meaning the mass of 1 mole, as we learned what the molar mass is. Okay, mass of 1 mole, number of moles. Okay, so this is N, another concept, number of moles, right? So I don't know if this kind of makes sense to you, because it's like a ratio. Okay, if you're calculating grams of a so here, remember that molar mass, right, is the mass of 1 mole. It's the mass of 1 mole. So let's just say the mass of 1 mole is 15. Now, in a certain amount of substance, you might not have 1 mole, right? Let's just say the mass of a substance is 45. 45 grams divided by grams per mole, okay, because that's molar mass, right? So if you're taking the molar mass at the bottom, right, which again is in grams, technically, but grams per mole it should be in, this molar mass is the mass of 1 mole. So if you take the mass of an entire substance, divided it by the mass of 1 mole, that should give you the number of moles. In this case, it's 3 moles. Okay, I hope that's kind of making sense to you. It's like a ratio, right? So it's like, if you want to know, the total mass of a substance, right? If you want to know the total mass of a substance, you know that there's 5 moles, and each mole is 20 grams. Okay, there's 5 moles, and each mole is 20 grams. So if you want to know the total mass of this substance, of course, you would then say 5 times 20, which would give us 100 grams. So you know that the substance weighs 100 grams. Its mass is 100 grams. Okay, so this is also like logic. That's why if you have to leave M alone here, you get N times big M. Number of moles times the mass of 1 mole, which is actually the molar mass. Number of moles times the mass of 1 mole is going to give you the mass of the entire thing. Mass of the entire thing divided by the mass of 1 mole is going to give you the number of moles. Okay, it's fine. If that's not making sense to you, it's okay. I just wanted to explain it for further explanation. Okay, but yes, that's the formula that we can use. It's a formula that includes moles, mass, and molar mass. Okay, so yes, let's move on here. Percentage of an element. So percentage composition, right? Let's just say we have H2O. Percentage composition basically is calculating how much H we have in H2O, or how much O we have in H2O. It's calculating how much of a specific element we have in a compound. So for example, if I have CH4, you can calculate the percentage composition of the carbon in the CH4, or you can calculate the percentage composition of the hydrogen in the CH4. Okay, the composition, the amount of a single element or an element in the entire compound. You're calculating the percentage of it. Okay, so that's why we have percentage of an element is equal to the total molar mass of the element divided by the molar mass of the entire compound. Always molar mass of the element over the molar mass of the entire compound. So let's look at this example. Consider these iron ores, hematite and magnetite, which contains more iron by mass. So they want to know which has the highest percentage composition of iron. That's how this question should be phrased. That's what they're asking. Okay, so it's important for you to understand. Okay, and you'll see I'm trying to work slow through these things so that I want you to get you to understand how these things work, because chemistry in high school is an incomplete syllabus, right? I'll be honest. It can get confusing at times because what you get taught, right? Or what you get taught, it's a weird word. What you get taught, okay? And then what you get asked is it's like a weird balance, right? It's not always like a one-to-one. You don't get taught A and they test you A. You get taught A, B, C, and then they test you Z, or the way they word it is confusing or whatever, right? So, and you see a lot of people when it comes to a subject like this, then they just memorize how to calculate things, right? Just memorize a formula, or like, okay, percentage composition is that over that, and then times 100. But if you understand it, it really makes it easier and you'll enjoy it a lot more, right? So again, percentage composition, percentage of an element. So the percentage, the molar mass of that specific element divided by the molar mass of the entire compound. So it's just a percentage. It's like your mark, for example, right? If you want to calculate your percentage mark, okay, you're going to take your mark divided by what? The total possible marks. If your test was out of 30, right? You say, what did you get? 27. 27 out of 30 times 100. So again, it's like a similar concept that you're calculating. Instead of your mark here, we basically have the molar mass of a single element, okay, divided by the molar mass, okay, of the entire compound. Okay, so again, it was like your total possible marks. All right, I'm not going to write it out. I'll just erase it. Okay, so I hope that's making sense. So yes, and in this one, they want to know which one of the two, hematite or magnetite, they're given Fe2 and FeO3, which one of the two has more iron by mass, which contains more iron by mass, so we can calculate the percentage composition essentially. So relative molecular mass, that's simple, right? Iron and oxygen. So iron, if we go to the periodic table and look for its relative atomic mass, okay, we're going to multiply it by 2. Iron, let's go to our little periodic table here. Look for iron. It should be in the transitional metals. Here's it here. It's 56. So we say 2 times 56 plus oxygen is 16. And this gives us the relative atomic mass of iron as 160. Okay, then percentage iron by mass. Okay, this table is not structured in the best way, but nevertheless, total molar mass of element in compound. So we want to calculate the percentage of iron, the percentage composition of iron specifically. So we take the molar mass of iron, which is basically 2 times 56. We divide it by the molar mass of the entire compound, which is 160. Maybe what we can do here is do another step. Calculator. Let's do another step. 2 times 56 is equal to 112 plus 3 times 16. This is equal to 48. And this gives us 160. So when it comes to doing it here, over here, we can just put 1112. So here, I can put 1112 because that is the molar mass of iron inside this compound. Remember, I have two atoms of iron, and I divide it by the molar mass of the entire thing. And I multiply it, of course, by 100, and I get a percentage of 70% on the dot. What a nice number. So the percentage composition of iron inside of hematite or FeO3 is equal to 70%. Let's calculate for fun the percentage composition of oxygen, percentage of oxygen in Fe2O3. This would be 48, because that's what the oxygen weighs. 48 over the whole thing times 100. And of course, we're going to get 30%. Okay, let's look at magnetite, and let's us calculate the percentage composition of iron inside this compound. That's going to be 3 times 56 plus 4 times 16. And that gives us 3 times 56 gives us 168 plus 4 times 16, that's 64. And in total, that gives us 232. This is grams per mole. Let's be good people and let's put units, grams per mole. Okay, so now how do we calculate the percentage of iron in the entire compound? You're basically going to take what iron weighs the mass of iron, the molar mass of iron, what iron weighs over what the entire thing weighs, and calculate it as a percentage. So 168 divided by 232 times 100. This gives us a percentage of 72%. If we had to calculate the percentage of oxygen in Fe3O4, all right, that would give us 64 over 232 times 100. And of course, we're going to get 28%. Okay, so to answer their question, which contains more iron by mass, that would be magnetite, because it has 72%. 72% of it is iron. Okay, so really simple. No need to complicate it. Okay, I know a lot of people might complicate percentage composition, but it's really simple. Mass of whatever you want to calculate the percentage composition of. So in this case, we did iron divided by the mass of the entire compound times 100. Okay, 3 marks, literally. Okay, let's look at this. Different types of chemical formulae. Consider the substance ethane, ball and stick model of ethane. It can also be represented using a formula. There are 3 types of formulas we use. Molecular formula is the actual number of each atom, and the empirical formula is the simplest whole number ratio of atoms. Structural formula shows us how the atoms are joined. Not so important for now. Mainly molecular and empirical formula, these are important things. Okay, so the actual number of each atom. So what ethane is actually, you guys will learn it next year in organic chemistry. Ethane is a hydrocarbon made up of carbon and hydrogen. Carbon's always the central atom, so these are carbons. Okay, so we have 2 carbons, so C2, and attached to these carbons are hydrogens. Okay, so we have C2H. If you count in total, it's 6. So this is a perfect formula for what we have. This represents this compound ethane, right? C2H6. It tells us exactly how much carbons, exactly how much hydrogens. That is what is known as a molecular formula, however. A molecular formula is the exact amount of each element in the specific compound, or what do they say? Actual number of each atom, the exact amount of each atom in a compound. Okay, molecular formula, C2H6. However, the empirical formula is when we then simplify that ratio. So C2H6 actually results in a 2:6 ratio, which results in a simplified 1:3 ratio when we divide both by 2. So that's what the empirical formula does. It is the simplest whole number ratio between the atoms. So C2H6 becomes C1H3, which is basically just CH3, right? You don't need to put that 1. So the empirical formula for ethane is CH3, but its molecular formula is C2H6. Molecular is the actual amount, the exact amount of atoms in that compound. And empirical is the simplest whole number ratio. So yeah, whole number. So we don't want like C1,5 H3. We don't want that, right? That's just not cool. Okay. So yes, that is the difference in definition between molecular formula and empirical formula. Okay, let us move on. And let us talk about concentration. We will discuss empirical and molecular formula in a bit, and the calculations. But for now, we're going to discuss a concept called concentration. So the concentration of solutions. Solutions are homogeneous mixtures of solute and solvent. The solvent and solute can be gas, liquid, or solid. The most common solvent is liquid water. Okay, so the solvent is the one in which the solute dissolves. So we have the solvent and going into the solvent is the solute. Okay, let's actually, I don't know. Let's just say this is sugar water. All right, let's just say we're putting a certain element inside of our solvent. We can call this the solute. Okay, and this entire thing, right? Once, okay, let's redraw it actually. Once the, oops. Once the solute is dissolved in the solution, in the solvent, these words are confusing. Once the solute is dissolved inside of the solvent, we call this the solution. Okay, so once the solute is dissolved inside of the solvent, we call it the solution. Okay, so yes, they say yes, solutions are homogeneous mixtures of solute and solvent. The solvent and solute can be gas, liquid, or solid. The most common solvent, so what is a solvent? The one that the other thing is getting dissolved in, this guy. The most common solvent is liquid water. This is called the aqueous solution, or AQ. Okay, right, look at this. We have a solution, salt and water. The solute is salt, the solvent is water. We have a solution, soda water. The solute is carbon dioxide, the solvent is water. Okay, cool, interesting. Let's look at concentration. The concentration of a solution is the number of moles of solute per unit volume of solution. The number of moles of solute per unit volume of solution. So this is basically the number of particles per unit volume. So it's saying the number of moles of solute for the volume of the entire solvent. Okay, that kind of makes sense. That tells us the concentration. Okay, so this is the definition. Right, then we have a formula. Sorry, okay, let me do this quickly. Okay, yeah, we have this formula. Okay, concentration, okay, in moles per decimeter cube. So now why is it in moles per decimeter cube? Because concentration is calculated by taking the number of moles and dividing it by the volume. So that just makes sense, right? If you want to know what is the concentration, how many of these things are in this specific area or specific region, you calculate the amount that you have divided by the total volume of that region. Okay, so in this case also number of moles divided by volume, the amount of moles there are in a specific given volume, that gives us the concentration. And why do we get moles per decimeter? Because it's moles per volume. So moles per decimeter to the -3. It can also be calculated with C is equal to M over C. C is equal to M over small m over big M times V. How do we obtain this? It's because, remember, moles can be calculated how? Moles can be calculated by saying small m over big M. These are moles. It's not exact, doesn't exactly look like a small n and a big M. It's a bit more different. Small m over big M, okay? And then you basically tip in times. You tip that. Am I doing something wrong? No. Oh yeah, you tip the bottom, sorry, it becomes, yeah, you tip, it becomes 1 over V, so therefore it becomes M. So that's how you obtain that formula, by the way. So you don't have to know this formula. In fact, I prefer not to use this formula. I don't know why. I just find it easier to even use the two formulas, just like because of an understanding purpose, it makes more sense to me. I know that once I have this, I can get my moles. Once I have my moles, I can get my concentration. That just logically makes more sense. But yes, ultimately, if you do have a mass in moles, you could calculate, or just mass in volume, sorry. Sorry, excuse me, you could calculate the concentration directly. Okay, this helps, especially if you don't have the moles. Okay, which you can calculate anyway, but yeah, nevertheless, that is a formula that we can use. Let's have a look, right? That is the number of moles of solute per 1 decimeter cubed of solution, that is moles per decimeter. If a solution has potassium permanganate, KMnO4, if a solution of potassium permanganate has a concentration of 2 moles per decimeter to the -3, it means that for every 1 decimeter cube of solution, there are 2 moles of KMnO4 dissolved in the solvent. I hope that kind of put it into perspective a bit better. Okay, so if it has 2 moles concentration, 2 moles per decimeter to the -3 of concentration, that means for every decimeter cubed of solution, there are 2 moles of the solvent, of the solute, sorry, yeah, of the solute dissolved into the solvent. Okay, and then let's have a look at this note, which gives us the conversion. So 1000 centimeters cubed is equal to 1 decimeter cubed, which is the same as 1 liter. So this is important. Volume to capacity. Okay, because sometimes they might give you the capacity, and actually not sometimes, a lot of the times you work with milliliters or liters. Okay, so therefore, yes, 1000 centimeters cubed is equal to 1 decimeter cubed, which is the same as 1 liter. Okay, and of course, then you could also deduce that it's the same as 1000 milliliters. Okay, that's also the thing. And 1 centimeter cubed is equal to 0.001 decimeters cubed. So the conversion is either to multiply by 1000 or divide by 1000. Okay, divide by 1000 when you're going to decimeters cubed, multiply by 1000 when you're going 2 centimeters cubed. Excuse me. Okay, then we also, it's given at the end that 1 centimeter cubed is equal to 1 milliliter. Muy importante. It's important. Okay, so let's have a look at some examples with calculations of concentration, just basic examples. So a solution contains 10 grams of sodium hydroxide, NaOH, 10 grams of sodium hydroxide. Please note that you need to get to a point where every time you see 10 grams, you should automatically in your head be like, hey, 10 grams, I can easily get the moles. If I have grams, I can get moles. Why? Because remember the formula, that's what I'm looking for. The formula that involves mass is moles is equal to mass over molar mass. And molar mass, we technically always know it. So you can just say this 10 divided by the molar mass of the substance, and you can easily get its moles. Okay, so just keep that in mind. So 10 grams of sodium hydroxide in 200 centimeter of solution. Calculate the concentration of the solution. So calculate the concentration. That's our ultimate objective. So you can even work backwards if you'd like. I know this is not Euclidean geometry, but you can work backwards. Okay. C is equal to N over V. So this is good because now you have a formula and the formula tells you what you need in order to calculate concentration. So C is equal to N over V. You need the moles and you need the volume. None of which you have. That's a lie. You actually have the volume. We need the moles. We don't have the moles. We have the volume. It's 200 centimeters cubed. By the way, which whenever we use these formulas, we have to convert to the SI units. And the SI unit for volume is decimeters cubed. Okay. What about the SI unit for moles? It's just mole. That's all for now. Sorry, this is for volume actually, not for concentration. Concentration is moles. It's written there on top, moles per decimeter to the -3. Because remember, again, it's moles and then decimeters cubed at the bottom. But yeah, it's decimeters cubed, so you'll have to convert it. Okay, before that, let's calculate the moles, because that's what we need in order to calculate the concentration. So how do we convert grams to moles? We have to understand, we have to use this formula. N is equal to M over M, which is equal to 10 over NaOH. So you can add it all in the denominator, that works fine. But let's go to our periodic table. Let's look for N, A, 23, O is 16, H is 1. So NaOH, it's going to be, let's do that. N divided by Na, we said was 23, plus O is 16, plus 1. So when we do the calculation, we get the moles as 0.25 moles. Now we have the moles. What moles? We have the moles that the moles of the 10 grams of sodium hydroxide. We all know it's moles. So now we can sub it into that concentration formula. C is equal to N over V, which is equal to 0.25. Let's convert V to decimeters on the right. So we can just say 200, basically divided by 1,000. This is equal to 0.2 decimeters cubed. So we say 0.25 divided by 0.2, and we get 1.25 moles per decimeter to the -3. So what does this mean? This basically means that for every decimeter that we have of solution, we have 1.25 moles of the solute. Okay, so that's what that means. I hope that makes sense. Please stop me if you have any questions. But yes, that's how we use N is equal to M over M and C is equal to N over V. Let's have a look at this. Calculate the mass of solution of solute in 600 centimeters of 1.5 moles per decimeter sodium chloride solution. So ultimately, they want us to calculate the mass, right? They want us to calculate the mass of solute. Okay, and the way we know mass from, we know mass from this formula. N is equal to M over big M. So we have big M, okay, and we want small m, so we need to get N, okay. What else do we have? We have the volume and we have the concentration. So there you should note that C is equal to N over V. If we sub in the concentration, we can calculate the mole. Sub in the concentration and the volume. Remember, it's 600 over 1,000. You don't have to show this. 0.6. So when we say N, it's actually going to be 1.5 times 0.6, and that gives us actually moles of 0.9 moles. Okay, so you see we're working backwards here, right? We give it volume and concentration, we can get moles. If you're given volume and concentration, you can get moles. If you're given just mass, you can get moles. If you're given volume and molar volume, you'll see we'll do that just now, you can get moles as well. So here we work backwards with the concentration. They gave us volume and concentration. We got moles. Now we can substitute it into that other equation. Small m over big M. What do we want? We want the mass, moles we just got, 0.9 is equal to the mass divided by the molar mass. The molar mass of what? Sodium chloride solution. Is that the same thing we worked with here? Yep. No, that is sodium hydroxide. Sodium chloride is NaCl. Cl is 35.5. Na is 23. Okay, these are things on the periodic table, which gives us our final answer of the mass of this sodium chloride solution as 52.65. And we use grams. And that's our final answer. Okay, so working backwards, this is using what? Using the concentration formula. C is equal to N over V, C is equal to N over V, as well as N is equal to M over M. Just basic calculations, right? When you're doing stoichiometry questions, you're going to have to do these, right? These are very common. Like you might get a question that asks you to do something very similar to this, like even if not exact the same, like same concept, or it could be a higher mark question, like 5, 6, 7 marks, where this is just like the first step, or this is maybe in a few steps, right? But you have to know how to use these formulas and understand them. Okay, and also what's also very important, you have to get used to the concept of when you have information, knowing what formula you can use that information with. That is actually very important. Okay, let's move on to molar volume of gases. Molar volume of gases. If different gases have the same volume under the same conditions of temperature and pressure, they will have the same number of molecules. Interesting. If different gases have the same volume under the same conditions and temperature and pressure, they will have the same number of molecules. Okay, the molar volume of a gas, Vm, is the volume occupied at 1 mole. So again, it's one of these constant things that we're working with, right? Because to work with the small amounts is just not possible. So we work with 1 mole. So we even have something called molar volume. So things we discussed in terms of the mole itself. So firstly was the mole itself. We discussed what the mole was, right? It's the 1 mole of something has the same number of particles as 12 grams of carbon-12. Then we discussed molar volume, which is the mass in grams of a substance, 1 mole of a substance. It's the mass in grams of 1 mole of a substance, right? Now we're dealing with this molar volume. It's the volume that a gas occupies, that 1 mole of a gas occupies. That is molar volume. Okay, so Vm, or molar volume, for all gases at STP is 22.4 decimeters cubed per mole to the -1. So we have something called the molar volume. Okay, at STP. STP is standard temperature and pressure. So these are important to know as well. STP is standard temperature and pressure. Standard temperature is 273 Kelvin or 0 degrees Celsius. Standard pressure is 1.013 times 10 to the 5 pascals or 1 atm, which is atmospheric something. I forget exactly. Let's do this. Let's highlight this differently. Standard temperature is that. And standard pressure is this. Okay, these are important to know. They can ask these, so you have to know it. The easiest one I always find to remember, standard temperature 0 degrees, and then this is 1 times 0.13 times 10 to the 5 pascals. Actually, no, I don't remember. Sorry, that 1 atmospheric pressure. So standard temperature 0 degrees Celsius, standard pressure 1 atm. Okay, cool. So, and that's also molar volume. This also means that this also means that for reactions at constant temperatures and pressures, gas volumes will react in the same ratio as the molar ratio. Okay, yeah, this is an important concept. So, all it is saying is, for all reactions that take place at STP, so if a reaction takes place, you'll see they'll mention it, right? This reaction takes place at STP. Okay, standard temperature pressure. So if it takes place at STP, the gas volumes will react in the same ratio as the molar ratio. So for example, okay, we have this equation. We have this chemical equation. N2 plus 2O2 gives us 2 NO2, right? So we know the molar ratio, we can see it. It's 1 mole, okay, if we ignore this, right? We know the molar ratio. What is it? It's 1 mole is to 2 moles is to 2 moles. 1 mole is to 2 mole, it's to 2 moles, right? That's just given by the molar ratio coefficient itself. So that's what's given here. 1 mole plus 2 moles plus 2 gives us 2 moles. So 1 mole of N2 plus 2 moles of O2 gives us 2 moles of NO2. So if we had to have what? If we had to have 1 decimeter cubed of N2, the gases, the volume of the gases would react in the same ratio as the molar ratio. So 1 mole and 1 decimeter would result in 2 moles, 2 decimeter, which produces 2. So if we had to have another example where we work with, for example, let's say 5 moles, 5 decimeters cubed of N2 is used. Because it's a 1:2, you would have 10 decimeters cubed of O2. Okay, giving us, again, 10 decimeters cubed of, what you might call it? Why is that not erasing? Okay, it's not showing on your guys' screen, so that's fine. Okay, so that's important to note, right? That when the reaction takes place at STP, okay, the gas volumes will react in the same ratio as the molar ratio. Okay, let's look at the formula that we formed from this molar volume thingy. Okay, we have a new formula. N, which is number of moles, is equal to V over Vm. V is volume of gas, okay, in decimeters cubed, just the regular volume that we always work with, okay. Vm is the molar gas volume at STP, okay, and N is the number of moles in moles, of course, right? So molar gas volume, so again, this is the amount of the volume of a gas, the volume of 1 mole of gas at STP. Okay, so this formula can only be used if the reaction takes place at STP. Otherwise, it's useless. Otherwise, you cannot use it. Okay, so if it takes place at standard temperature pressure, which is STP, then we can use this formula. Okay, and generally, the constant that we use for Vm is 22,4. However, many times actually, so if it's not given, if they don't tell you, if another molar volume is not given, you will use 22,4. However, sometimes they do give another molar volume, then you use that one that they give. Okay, so again, Vm, the volume of a gas, the volume of 1 mole of gas. Excuse me, the volume of 1 mole of gas at STP. Okay, cool. Right. Now, let's quickly end off on this question. Example, a gas jar with a volume of 224 centimeters cubed. So we know the volume. Okay, this is regular volume, right? Let's do it in this color. Is full of chlorine gas at STP. Keyword what? At STP. How many moles of chlorine gas are there? Okay, how many moles of chlorine gas are there in this gas jar? Okay, so a bit of a weird question, but nevertheless, they want us to do the simple calculation of calculating the moles at STP. Moles at STP, whenever you see STP and volume, the first thing that should come to mind is this guy, this formula here, because this is the only time you can use it at STP. So when they say at STP, the likelihood of you using this formula is high, because again, you can only use it at STP. So if they want to test you this formula, they have to use STP. Okay, so the volume of the gas jar is 224 centimeters. We divide this by 1,000. We get 0,224, I believe. Right? That's 0,224 decimeters because we have to use SI units. Okay, then we can use this formula. N is equal to volume over molecular volume, which is, we just got the volume 0.224 divided by molecular volume, which is 22.4. That is a constant. Okay, they gave us nice values here so that we can get like 1 somewhere there, but not always going to be like that. Okay, so that's a constant. We can get it from our constant values in the back of our paper. Right, or alternatively, if they give you one, if they say use the molar volume as 24, then you should use it as 24. Don't now use 22.4 if they tell you to use it as something different. However, if they don't specify, then you use 22.4. Okay, when we do this calculation, the number of moles, we get 0.01 moles. Okay, 0.01 moles. What is this? This is the moles of chlorine gas in the gas jar, because it's at STP. They gave us the volume of the gas jar, and it's full of chlorine gas. So we say that volume, the actual volume, divided by the molar volume, that gives us the amount of moles, full at STP. Perfect. Okay, so that is that, right? I hope that you guys understood what we were doing, and we covered the basics of stoichiometry well enough. Okay, so molar mass, percentage composition, concentration, and volume, right? And then VM as well, molar volume, right? Next, we'll move on to these, right? Some more complicated calculations, water of crystallization, calculating the empirical formula of compound from mass, calculating it from percentage composition. Another example, empirical to molecular, balanced chemical equations, whatever. And then eventually, obviously, we want to get to limiting reagents, percentage purity, percentage yield, and then we're done. A lot of stuff to cover, right? But nevertheless, let's end it there, and we will continue. We will meet on Monday, don't forget. All right, we will continue with this. So yes, indeed. Thank you guys so much for joining. I hope that you guys have a good holiday, and that, yeah, I'll see you guys on Monday either way. But yeah, have a good holiday, and hopefully it's beneficial and constructive resting so that you can go back into school fresh and ready. But yeah, cool. Thank you guys again. I will see you guys on Monday. Jazakallah khair. Assalamu alaikum and goodbye.